Hey guys, Mr. Smine, and today we are going to talk about estimation and significant figures when we're using measuring tools in the lab. So in this video we're still working on the essential question of what is matter and how do scientists observe it. Specifically in this video we're going to answer the questions: how do you record measured values to reflect the precision in the measuring tools you are using, and how do you record calculated values to reflect the precision in the measuring tools that you used. First, we're going to start out by defining two different terms, and that's accuracy and precision. When we're talking in the regular day language, we think of these two words as the same thing, but they really have different definitions. Accuracy is how close your measurement is to the actual value you are measuring. So if an object has 25 milliliters of volume, so it takes up 25 milliliters of space, exactly 25 milliliters of space, your accuracy is determined by how close you are to that actual 25 milliliters. Precision is a little bit different. Precision is how close multiple measurements are to each other and how much uncertainty there are in your measurements. So if you take that same 25 milliliter object and you measure it 5 times, the closeness of those measurements to each other reflects your precision. Precision is also how uncertain your measurements are, and that's reflected by the measuring tools that you use. The more precise your measurements are means that they're less uncertain, the less uncertainty they have. So here we see 3 different measuring tools that you'll use in the lab. On the left is an example of a 50 milliliter graduated cylinder. In a 50 milliliter graduated cylinder, each line represents 1 milliliter. As we talked about in the volume video, when you're measuring using a graduated cylinder, you're going from the bottom of that meniscus and you're using that to record your value. Anything that falls between 2 lines or is closer to the middle of 2 lines, we're going to record as 0.5 of a milliliter, and anything that falls closer to the line is 0.0. Our last measurement is always an estimate. If we compare that 50 milliliter graduated cylinder to the one on the right, which is an example of a 10 milliliter graduated cylinder, the 10 milliliter graduated cylinder, each line represents 1/10 of a milliliter. So when we record values using the 10 milliliter graduated cylinder, we're either going to 5/100ths of a milliliter or 0/100ths of a milliliter, depending on whether it's closer to the line or between the lines. So if we compare the 50 milliliter graduated cylinder on the left to the 10 milliliter graduated cylinder on the right, we see the 10 milliliter graduated cylinder is more precise. And that's because we're estimating to 1/100th of a milliliter with a 10 milliliter graduated cylinder, where we're only estimating to 1/10 of a milliliter in the 50 milliliter graduated cylinder. So the 10 milliliter graduated cylinder has less uncertainty. On the right we see a ruler, and we see a red bar being measured by that ruler. So each numbered line on the ruler represents 1 centimeter. Each centimeter is divided up into 10 smaller sections that we call millimeters. Because the last digit that we record is an estimate, we estimate to 1/10 of a millimeter using a ruler. So looking at this red bar, I can see that this red bar falls somewhere between 2.3 centimeters and 2.4 centimeters. I would record this as 2.32 centimeters. That last 2 is an estimate. When we see a recorded value of measurement, not only do we get an idea of how much mass it had or how long it was or the amount of space that it took up, we also get an idea of how precise the tool was that was used to measure it. So let's take a look at these 3 volumes as an example, thinking about precision. So looking at the first value, 43.5 milliliters, I know that whoever was measuring this probably used a graduated cylinder that had 43 measured and 44 milliliters measured, and that the volume of whatever they measured fell somewhere between 43 and 44 milliliters. So that 0.5 is an estimate. Looking at that second measurement, 12.60 milliliters, I know that the tool that was used to measure that had 0.6 milliliters on it and 0.7 milliliters on it, and whoever measured it thought that it fell closer to the 0.6 milliliter line. If we compare the first and the second value, we would say that 12.60 milliliters is a more precise measurement. They were able to estimate out to further values, to the hundredths of a milliliter rather than tenths of a milliliter. If we look at the third value, 12.600 milliliters. You may be thinking to yourself, now 12.60 and 12.600 are the same value. And that's true, they are the same value, but looking at that third measurement, 12.600 milliliters, that's measured using a more precise tool. So we already saw that it's really important that the last number that you use, that you're always estimating the last number that you record when you're measuring something, whether it be using a ruler or a graduated cylinder. Sometimes when we're finding volume, we have to calculate. And when we calculate, we also need to make sure that our calculations reflect the precision of the tools that we used. So we're going to show you how to do that, how to record so that your precision is reflected in your calculations. First of all, we need to realize that there's two different types of numbers. There's exact numbers and there's measured numbers. If I say that there's 18 kids in your class, that's an exact number because I counted. It's not like there's 18.1 kids or 18.4 kids. There's exactly 18 kids. Whereas if I measure something, if I say a piece of string is 13.4 centimeters long, that's a measured value. I know that 0.4, that last number, is an estimate, so that makes it different than that exact number when we counted the number of kids. So when we're calculating numbers and we're thinking about reflecting the precision of the tools that we use, we're only going to do that for measured values, not exact values. So if I add together the number of kids in your class with the number of kids in a different class, I don't need to think about making sure that my precision is reflected because those are exact values. Whereas if I'm calculating volume by multiplying length times width times height, I do need to make sure that my precision is reflected in that. When determining how to go about reflecting the precision in the values of the tools that you used, the first thing that you need to do is make sure that you have measured values, that they're not exact values. Once you've done that, once you've determined that they are measured values, you need to decide whether you're doing addition and subtraction or multiplication and division. So addition and subtraction uses different rules than multiplication and division does. When using addition and subtraction for measured values, the first thing that you're going to do is determine which measurement that you're using has the least number of places after the decimal. Once you've done that, you're going to add or subtract the numbers together, and your answer should have the same number of places after the decimal as the value, the measured value, with the least number of places after the decimal. So let's take a look at what this looks like. In our first example, we're going to use the data that we had from the volume video. In the volume video, I showed you how to find the volume of an irregular shaped object. To do that, I had to find two volumes. One was the initial volume of water that we had in a graduated cylinder, and the other was the amount of volume, the amount of water, and an irregular shaped object. So when I did that, I started with 32.0 milliliters in the graduated cylinder. When I added the object, I got 35.5 milliliters. And we said to determine the volume of that irregular shaped object, we had to subtract those two values from each other. So already I know that I'm doing subtraction. I'm going to look at both of those values and I can see which one has the least number of places after the decimal. This is pretty easy in this example because they both only have one place after the decimal. So my answer should only have one place after the decimal. I would then go to my calculator and put in 35.5 milliliters minus 32.0 milliliters, and it would show me that the difference between those is 3.5 milliliters. I'm just going to double check to make sure that my answer has the same number of places after the decimal as the measured value with the least number of places after the decimal, and it does, so that works out. Next example is a little bit more tricky. So here I have 24.7 milliliters, and I'm going to subtract 6.70 milliliters. So you can see that 6.70 milliliters was measured using a more precise tool than the first measurement. When I put those values in the calculator, I get 18.00 milliliters. But looking back, 24.7 milliliters only has one place after the decimal, so I need to make sure that my answer only has one place after the decimal. So I change from 18.00 milliliters to just 18.0 milliliters. In the last example, I have 13.4 milliliters and I'm going to add 3.45 milliliters. When I put that in the calculator, I get 6.85 milliliters. Now looking back, I see 13.4 milliliters only has one place after the decimal. So I'm going to need to only have one place after the decimal in my answer. So I need to get rid of that 5 at the end. And to do this, I'm going to round. So when I'm rounding, any value higher than 5, I'm going to round up. 4 and below, I'm going to round down. So 16.85, I'm going to round up to 16.9 milliliters. When we're multiplying and dividing, it gets a little bit trickier making sure that our precision is reflected. So the first thing that we need to do is we need to determine the number of significant figures, the number of values that are actually significant in our measurement. Then we need to report the same number of significant figures as the measurement with the least amount of significant figures. I'll show you how this is done. So the first thing that we need to realize is that some numbers are significant in our measurements and some aren't. So to determine whether they're significant, we're going to follow these rules. First off, all numbers that are not 0 are significant. So that's pretty easy. Really, we only need to memorize the rules for zeros, because sometimes zeros are significant and sometimes they're not. So to help us remember this, I divide zeros up into 3 different categories. I call them leading zeros, captive zeros, and trailing zeros. So leading zeros are before a non-zero number. So for example, the 0.034, those first 2 zeros are leading zeros. They're before the 3, which is a non-zero number. Leading zeros are never significant. They just hold the place of the measurement that we're using. Our second type of zero are captive zeros, and captive zeros are between 2 non-zero numbers. So the 0 in 103 is a captive zero. It's between the 1 and the 3. The 0 in 5.025 is a captive zero. It's between the 5 and the 2. Captive zeros are always significant. Trailing zeros is where it gets a little bit tricky. Trailing zeros come behind non-zero numbers. So in 12,000, the last 3 zeros are trailing zeros. In 1.3400, the last 2 zeros are trailing zeros. And trailing zeros are tricky because sometimes they're significant, sometimes they're not. When trailing zeros follow decimal point, they're significant. When they do not follow decimal point, they are not significant. We'll take a look at some examples. So the first example that we have here comes from when Miss Berna showed us how to find the volume of a cuboid. So she measured the length and the width and the height. So we have 3 measured values that we need to multiply together. When we put them in our calculator, we get 68.46627 centimeters cubed. Obviously, that value shows way more precision than we were able to use using the ruler that we used in the lab. So we need to change that to reflect the precision of the ruler that we used. So looking at the 3 measured values, 8.52 are all non-zero numbers, 3.28 are all non-zero numbers, 2.45 are all non-zero numbers. So all 3 values have 3 significant figures. So I need to change my answer so it only has 3 significant figures. So I'm taking 68.46627 centimeters, and I'm going to change that so it only has 3 significant figures. I'm going to change it to 68.5. So I round it up from 0.4 to 0.5 because that last value is a 6. I'm rounding up for 5 and above. In the second example, we get a little bit more tricky. So 108 centimeters times 0.014 centimeters times 1.384 centimeters. All 3 are measured values. I am multiplying, so I need to determine the number of significant figures for each value. 108 has a 0 in it, but it's a captive zero. Captive zeros are always significant. So 108 has 3 significant figures. 0.014 has leading zeros. Those leading zeros are never significant. 1.384 centimeters has all non-zero numbers, so it has 4 significant figures. So the value that has the least amount of significant figures is 0.012, which has 2 significant figures. I need to change my answer so that it only has 2 significant figures. When I put it into the calculator, I get 0.209268. I need to change that to 2 significant figures, so I change it to 0.21 centimeters cubed. Remember that leading 0 in 0.21 centimeters cubed is not significant. So an even trickier one is the third example here. So I have 2 measured values, 0.253 centimeters and 120 centimeters. Because these are 2 measured values and we're multiplying, I need to determine the number of significant figures for each of the measured values. So 0.253 has 3 significant figures. That leading 0 is not significant. And 120 centimeters has 2 significant figures. The trailing 0 is not significant because there's no decimal. When I put that in my calculator, I get 30.36 centimeters squared. I need to change that 30.36 centimeters squared so that it has 2 significant figures. So I changed it to 30 centimeters squared. But looking at 30 centimeters squared, I realize that it only has 1 significant figure. That trailing 0 is not significant because there's no decimal point. So what I can do is I can change it to use scientific notation. So I change from 30 centimeters squared to 3.0 times 10 to the 1 centimeters squared. Those two are the same values, but 3.0 times 10 to the 1 has 2 significant figures because there's a leading 0 with a decimal point. So to recap, in recording measured values so that they reflect the precision of the tool that we're using, we always make sure that our last number, our last digit that we record, is an estimate. When we're doing calculations, we also have to reflect the precision of the tools that we're using. To do this, we need to determine whether we're doing addition and subtraction, or multiplication and division. If we're doing addition and subtraction, we're counting the number of digits after decimal place, and we're using the least amount of digits after the decimal place as the measured values. In multiplication and division, we have to determine the number of significant figures. We're using the least amount of significant figures as the measured values in our final answer.